Hey, welcome back to Abstract Algebra. In this video lecture, we're going to look at the material in the second section of the symmetric group chapter 3.2, and I want to tell you something about something called cycle decompositions. Okay, so you're looking at the goals of the lecture there. I'll just kind of outline them for you real quick. I want to define something called the orbits of a permutation. The permutation sigma in Sn has orbits. I want to tell you what those orbits are. I want to define some other terms, cycle, disjoint cycles, and show you something called cycle notation that can facilitate computation. And then I want to prove a couple of theorems. I want to prove theorem 3.22 in your text. That's about decomposing a permutation into a product of cycles, disjoint cycles. I want to prove 3.24. That's about how to compute the order of an element in a symmetric group. All right. So let's get right to it. I'm going to talk fast through this, trying to keep the video short. You can pause it and think about the things that I say so that I'm not talking at you at a mile a minute. And I want to start by just recalling that if you give me a permutation in Sn, it gives rise to an assert equivalence relation on the index set by saying two indices are equivalent if some power of sigma sends one to the other. Okay, and those equivalence classes are called the orbits of sigma. So the orbits of sigma are just the equivalence classes of in that equivalence relation. We did this in the Zoom meeting. Let's take a look at what it looks like if we do it together right here. If you pick one of the elements in the index set, say 1, well, sigma of 1 is 3, sigma of 3 is 5, sigma of 5 is 1. Okay, so those three elements then comprise the orbit 1, 3, 5. Those are the elements that sigma can send to themselves, starting with 1. If you pick another element like 2, sigma of 2 is 2. So 2 is the only element it's in orbit. Every power of sigma is going to send 2 to 2. So I just keep doing this. I pick an element that I haven't colored yet. There's 4. Sigma of 4 is 6. 6 goes to 4. So 4 and 6 make an orbit. Pick one more. I can choose an element that's not in any element or orbit yet. 7. 7 goes to 8, which goes to 7. So there's the last orbit. Okay. So this function has, this sigma has 4 distinct orbits, and they have in them respectively 3 elements, 1 element, 2 elements, and 2 elements. So that's what I mean by the orbits. They're the equivalence classes under that equivalence relation. Let's keep that in view while we make it through this definition. So I want to tell you what I mean by a cycle. A permutation, I'm calling it gamma. It's called a cycle if this is kind of a mouthful, but if it has at most one orbit containing more than one element. Okay, and in that case, the length of the cycle is the number of elements in its non-trivial orbit, its orbit with more than one element. All right, our sigma above is not a cycle because it has 3 orbits with more than one element. So it's not a cycle. Let's check out this example. I've got a permutation gamma here. Let's find its orbits. I'll have to write them down as we go. Could do it with colors first. So starting with 1, it goes to 7, which then goes to 8, which goes to 2, which goes to 4, which goes to 5, which goes back to 1. So there's one of its orbits. 1 went to 7, which went to 8, which went to 2, which went to 4, which went to 5, which went back to 1. Close up the orbit. Okay, choose another color here. I see an element not colored. It's 3. 3 is fixed, so it's its own orbit. I see an element that's not colored anything. It's 6. 6 is fixed. It's also its own orbit. Now every element is colored. That is, we have every element in an equivalence class. And I can see that there is precisely one orbit with more than one element in it. And so that gamma is a cycle. Okay. I want to tell you what cycle notation is. Cycle notation just kind of means, in a permutation like this gamma, there's a lot of information that we kind of don't need to write. When we write cycle notation, we're just going to write it as a list of numbers, not separated by commas, and you're just going to write the elements of the orbit in the order that they occurred as you kept applying sigma. So starting with 1, we got 7, and then we got 8, and then we got 2, and then we got 4, and then we got 5, and you end it. Any number that's not there is understood to be fixed, yeah? So the 3 and the 6 are not there. I have to understand which symmetric group this is a part of. It's in S8, because without knowing this 8, I don't know what elements aren't there. But if I know we're in S8 and you show me the numbers 1, 7, 8, 2, 4, and 5, then I know we're missing 3 and 6. So those are the ones that are fixed, okay? And in this cycle notation, it's not unique. You can write the elements in that order. It's still the same permutation, because in all cases, it says that 7 goes to 8, which goes to 2, which goes to 4, which goes to 5, which goes to 1, which goes to 7. Yeah, so you can cyclically permute the elements in the cycle notation and you don't change the cycle. That's why we call them cycles. Cool. You might be wondering about this annoying at most 1. Why not just say exactly 1? Well, because if we take the cycle, the orbits of the identity permutation, the orbits of the identity permutation are all singletons. Yeah, the identity fixes every single element. And so it has no orbits of containing more than one element, but I still want to call the identity permutation a cycle. It's a cycle of length 1. You can just put any element in there that you like. 1 goes to 1. It's a cycle of length 1. Okay. Some more terminology. I'm going to call 2 cycles disjoint if their non-trivial orbits are disjoint. Okay, so getting you used to the notation down here. I've got 2 cycles here. Let me give them names. Let me call them like gamma 1 and gamma 2. Gamma 1 sends 1 to 3, 3 to 7, and 7 to 1. You could write it as an array notation. So it's understood in S10 that it would fix 2 and 4 and 5 and so on, all the way up to 10. It fixes everything but 1, 3, and 7. Gamma 2 sends 2 to 4, 4 to 6, 6 to 8, and 8 to 2. Notice that no element, quote unquote, moved by gamma 2 is moved by gamma 1 and vice versa. So that's what I mean by their disjoint. I'm going to leave this result to you, lemma 3.21 in your book. I'm going to leave the proof of it to you as an exercise, but the exercise says that if you take 2 disjoint cycles, they'll commute. You can start trying to prove that exercise. Show yourself that gamma 1, gamma 2 is the same as gamma 2, gamma 1. Those 2 cycles will commute because they are disjoint. Okay? Of the 2 theorems that I want to prove here for you today, one of them is that every permutation can be written as a product of disjoint cycles. You can break a permutation down into a product of disjoint cycles. So I just want to illustrate that here with this permutation that we've been talking about, this sigma. We already wrote its orbits, yeah. Its orbits were written above. I can just kind of color code them again real quick here. There's the orbit with 3 elements in it. There was the element that had just a singleton. There was these 2 element orbits, and there were 2 of them. Oops, can't use that color again. Let's use this one. All right, so the orbits are the colors, yeah? The orbits got 1, 3, 5. There's an orbit with 2, an orbit with 4 and 6, and an orbit with 7 and 8. So if I define some permutations like this, let's say I take a cycle and I just let it send 1 to 3, which is sent to 5, which is sent back to 1. Then that cycle, I'll call it gamma 1, is behaving exactly like sigma does inside of that orbit. All right, fixes everything else. So this gamma 1 fixes 2, fixes 4, fixes 6, and so on. There's another cycle, sends 4 to 6, which is sent back to 4, and a third one, which interchanges 7 and 8. So I've kind of daringly claimed that that equals sigma. Here I've written a product of 3 permutations. And just to kind of convince you that it works, let me just sort of try to write out the array down here. So let me write the numbers 1, 2, 3, 4, 5, 6, 7, and 8 in order. And then just one at a time, let me try to compute, always going right to left, yeah? So let's see what this thing does to 1. Okay, well, so you got to be looking with me over here when I'll just do it for this one element. This cycle 7 and 8 interchange, it fixes 1. 1 goes to 1 because 1's not there. This also fixes 1. And then this guy, well, it sends 1 to 3. So at the end of the day, 1 went to 3. Yeah. And you see that if we choose the element, say 3, it's going to do the same thing. 3 is fixed, 3 is fixed, 3 goes to 5. So 3 will go to 5. How about 5? 5 is fixed, 5 is fixed, 5 goes to 1, so 5 goes to 1. Pick an element like 2. 2 is fixed, it's fixed, it's fixed. I'm just reading right to left when I say these things. Fixed, 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 so 2 is fixed. What happens to 4? 4 is fixed, it's sent to 6, which is fixed, so 4 goes to 6. All right. So if you continue this exercise, you'll convince yourself that, yeah, you exactly recover sigma. You exactly recover sigma. That is the essence of theorem 3.22. Theorem 3.22 says that every permutation in Sn, every sigma in Sn, every sigma in Sn can be written as a product of disjoint cycles. Okay, so let me try to walk you through a proof of that. Slightly different than the argument that the author gives in the book. You should compare them. So give me a sigma, and it's got orbits, right? So I denote them B1 through BR. I don't know how many orbits there are, so I just say there's R of them. And what do I know about these orbits? Well, together they make up the entire index set, and no two of them have anything in common, yeah, because they're equivalence classes. So let's pick a value of K between 1 and R, all right? Pick an orbit, if you like. And I'm going to define a permutation that I'm going to call gamma sub K. At first, it's just a function. You're going to show it's a permutation, but I'm going to define a permutation gamma sub K by the following. So I got to tell you what gamma sub K does to an index. Well, it depends on whether the index is in the kth orbit or not, all right? So if the index belongs to the kth orbit, then gamma sub K of that index is sigma of it. Otherwise, it fixes it, all right? I'll kind of maybe interrupt the proof to go back up here. This is sort of what I did. If you look at, say, the indices that are in the yellow orbit, yeah? So I'm just letting, say, gamma sub 1 be that first orbit has 1, 3, 5. Gamma sub 1 does the same thing that sigma does to those elements, but it fixes everything else. This would be my gamma sub 2, and this would be my gamma sub 3. All right. Any fixed point, I won't even write that cycle. The element that fixes everything is just the identity. I'll leave it out of our product. Okay. So back down to the proof. That's how I'm defining these gamma sub k's. I'm going to leave it as an exercise to you that those things are actually permutations, and they're disjoint, and they're cycles. They were cooked up to have one orbit each. They were cooked up to be disjoint because I'm using the orbits to make them, and the orbits are disjoint. And you have to show that they're one-to-one and onto, show that they're permutations. So we can talk about it in an office hour, but I'm just going to move on now. So I have a claim. I claim that if we multiply those gammas that we made, we're going to recover sigma. You've already seen that happen. This is what we did. We recovered sigma up there, yeah? So let's see if we can't do it in general here. So how do I do that? Okay, so pick an index, because what is my claim? My claim is that two functions are equal, right? I've got a function called sigma, and I've got a function called gamma 1 times blah, blah, blah up to gamma r, and I'm claiming they're equal. So the only way to show two functions are equal is to show they do the same thing to every input. So I'm picking an input j. And remember the orbits partition. So there's a unique orbit that contains j. J is in exactly one orbit. Let's call it the kth one. Okay, so then sigma of j by definition is gamma sub k of j, And that's also in the kth orbit, right? When sigma moves you to something, you don't leave the orbit. You're still in that same equivalence class. Cool. So if you choose an index that's different than k, well, then either gamma sub, sorry, not either, but gamma sub I of j is going to be j, because j is not in the ith orbit, and also gamma sub I of sigma of j, of gamma k of j is also going to be a sigma of j, gamma k of j, because that's also not in the ith orbit. Okay, so when you feed this j into your function, you'll start giving it to these gammas. And if the index isn't k, then the corresponding gamma just gives you that index back. Eventually, you're going to hit the index k. I don't know where it is, but when you do, you'll get gamma k of j, because we're in that orbit. But then the rest of these functions will fix that. So when the process is all said and done, oops, that was not what I wanted to do. When the process is all said and done, you're going to get gamma sub k of j out, and that's sigma of j. All right? So that's actually the proof of that theorem. We can talk about it. Let's move on. This video is getting probably a little long. I don't know how long it is right now, but I want to keep it as short as possible. So let's look at this last theorem, the theorem about computing orbits. And I'm going to locally in this class for the rest of this semester, I'm going to refer to this as Megan's theorem, because in our online Zoom meeting today, Megan guessed at this. She computed the order of a sigma by telling us, well, she took the least common multiple of some numbers, and that's precisely what this theorem says. If you take your sigma and you write it as a product of disjoint cycles, we just proved that you can always do that. And let's say that they have these lengths, M1, M2, up to MR. Then the order of your sigma is their least common multiples. So that's what Megan told us in class today. She took the least common multiple of 3, 2, and 2 and got 6. And sure enough, that sigma had order 6. So that's why we're going to call this Megan's theorem. Okay, so how to prove it? Well, let's have a go. Take your sigma and write it as your disjoint cycles, okay? Let's say gamma k has length k and they're disjoint. Cool. Well, so first of all, the order of a cycle of length mk is mk. If you're going to compose a cycle with itself, then you won't get the identity until you compose it with itself its length number of times. So that means that if you raise gamma sub k to the m, you could get the identity if and only if that length, that order, divides m. All right, so that's just a basic group theory fact, that a power of an element is the identity if and only if the order of that element divides the power. So then let m be the least common multiple of all those things. So in particular, mk divides m for every k. Okay, well then, since disjoint cycles commute, if I look at the mth power of sigma, I can drop in my product. And since these things commute, the mth power of this product is the product of the mth powers. In each case, because mk divides m for every k, every one of those things is going to be the identity, and the product of a bunch of identities is the identity. All right, so what does that show? It shows that it doesn't take any more than the power m to kill sigma. Sigma to the m is the identity, so its order can't be more than that. So how do I get the reverse inequality? Well, suppose that you have some power of sigma that's the identity. Again, because these cycles are disjoint and they commute, that would imply that gamma 1 to the n times gamma 2 to the n and so on down to gamma r to the n was the identity. But the gammas are disjoint. They're disjoint. So if their product is the identity, every single one of them has to be. That's something that I kind of want to leave as an exercise for you, but it comes from the fact, if this weren't the identity, then there would be some index that it sent to something besides itself, right? And that index would not be touched by any of the other gammas. So if gamma sub k of n moved something, so would sigma. Sigma would move the same thing. Okay, so we should talk about that detail, but I'll just leave it at that here in this video. We said mk was the order of gamma k. So if gamma k to the capital N is the identity, mk has to divide it. Well, if mk divides n for every k, then n must be greater than or equal to the least common multiple of all those mk's. So there's your opposite inequality, and that's how you can compute the order of a permutation. You can break it down into its cycles, and then you just take the least common multiple of the lengths of those cycles, and that number is your order. Okay, I'm going to stop this video now. I know I was talking fast. I hope you paused it a lot, and I hope you'll come to class tomorrow where we can talk about these same ideas in real time.